Warm greetings to everyone present here. I'm Nisha from Caterpillar, and I'm here to shed some light on lane detection using deep learning. But before that, let's begin with a little bit of introduction about myself. I'm from Coimbatore, a district in Tamil Nadu, which is also known as Manchester of South India. I've done my bachelor's in electrical and electronics engineering. I'm creative, energetic, confident, and constantly looking for opportunities to learn and explore. I'm currently working as data analyst at Caterpillar. I joined Sweet this year, which has really helped me in strengthening my network and is also inspiring me to be the best version of myself. With that, let's move to the agenda. My topic for the day is lane detection using deep learning. But before we get into any of these, either lane detection or deep learning, let's begin with what is artificial intelligence and some of the aspects of artificial intelligence. We will begin with what is artificial intelligence, why is it required? We'll take a step further and understand what is machine learning, which is a subset of artificial intelligence. We'll also understand some of the challenges in implementing machine learning and how is it solved using representation learning and some of the challenges, which is again available in representation learning or downsides of representation learning, which is solved using deep learning, which is a subset of machine learning. After which we start with our algorithm, which is used to detect lane. The approach which I've used is I've used series of convolution neural networks along with instance segmentation. To understand what is convolution neural network, we'll discuss about what is convolution operation. We'll move on to instance segmentation. To understand what is instance segmentation, we'll talk about various computer vision tasks which are available, for instance, object classification, semantic segmentation, object detection, etc., including semantic segmentation. After which we'll talk about the downside of a brute force method, which is used to solve this problem and how to solve it. Later on, we'll get into why are we going to hear the word deep learning more frequently in near future. We'll also touch upon some of the interesting and surprising applications of artificial intelligence, which is already there out in the real world, saving and serving us. So with that, let me begin with a question. What is your interpretation of artificial intelligence? Please use the chat feature to answer the question. As you might have guessed, it's the ability of machines to exhibit intelligence like human beings to perform tasks that are typically performed using human intelligence. Now, why do we want to do this? During initial stages, we said there is a problem which is mathematically complex in nature. So there is a scope of human error. We want to avoid human error. We're giving it to the machine to understand it. Why does machine require intelligence? That brings us to the importance of artificial intelligence, wherein we look to automate routine labor, understand speech or images, make diagnosis in medicine, support basic scientific researches. During initial stages of development, artificial intelligence tackled and solved problems that are intuitively difficult for human beings to solve, but is relatively straightforward for machines, because those are a set of problems which can be described using a set of mathematical rules or formulas. The real challenge for artificial intelligence proved to be solving some of the problems which is straightforward to us, but it's difficult for us to describe it using a set of mathematical formulas or rules. And it feels intuitive to us. For instance, recognizing spoken words or faces in images. Let's move on to machine learning. Machine learning is the science of programming computers to learn from the data. It's also known as the ability to learn without being explicitly programmed. A more engineering-oriented definition for machine learning would be a computer program is set to learn from an experience E to perform a task T, measured with a performance measure P. If its performance measure P, measured at task T, improves with experience E. To understand this better, let's consider a real-world example. Let's consider classification of email as spam or ham. The example which the algorithm uses to learn is called as a training set, and each example in a training set is known as a training instance. This is the experience of the data set. The task is to classify the email as a spam or a ham. The performance measure is yet to be defined. Let us consider correctly classified emails ratio as the performance measure. This metric is known as accuracy and is most commonly used in classification tasks. Now, there are broad categories of machine learning which are defined based on certain criteria. There's going to be 3 criteria which we're going to discuss. So one is based on the level of human intervention which is required to train these algorithms, based on which we see in the image here, it's called as supervised learning, unsupervised learning, reinforcement learning, semi-supervised learning also. And the second criteria would be whether it can learn on the fly when it's added data, which is known as online learning versus batch learning. The further category would be to understand whether the algorithm is classifying a new data point based on the already known instance, which it has already seen, or it has formed a pattern, already known data points, and it's tried to fit in this new data point in that pattern, based on which it's known as instance-based learning and model-based learning. Now moving on to supervised learning. In supervised learning, the input data is fed along with a label or target, which is the desired output. A typical supervised learning task would be classification of email to predict whether the given email is a spam or ham. In this instance, we would provide the algorithm with various learning examples, which contains its desired label also, whether the mail is a spam or ham. And the algorithm is expected to predict if a new email is given, whether it's going to fall under a spam category or a ham category. Another typical task is to output a numeric value. It could be either a price of a house or a price of a car. And to understand how to predict price of a house or a car, we need something called features. In case of predicting the price of a house, we might require features such as area of the plot, number of rooms, proximity to the city, and other features which are available. And to predict price of a car, we might require mileage, age of the car, brand, etc. Now we're feeding this algorithm with multiple instances which contains mileage, age, brand, and its desired price. Now if we provide a new value, which is either from the data set, training set already, or a new instance, it should be able to give us the price. This task is known as regression. Now moving on to unsupervised learning. In this type of learning, we provide the algorithm with inputs which contain just the data but not the desired label. Now the algorithm is expected to group the data together based on certain attributes, which is common among the data. For instance, in this picture, we see that apples are grouped together and watermelons are grouped together because they have certain features, let's say oval shape for watermelon or the shape of an apple, color of an apple, certain criteria like that. Real world example of unsupervised learning would be anomaly detection. Let's assume that you're using your credit card today from day to night, and your recent transaction would be tonight sometime, and you've used it in India. If the bank detects that early morning tomorrow it's being used in Antarctica, let's say, then the location variation is very high. You see that among all the data points which is already available, all your transaction, let's say all your transaction falls within India and within a particular state, for instance. In that case, the location variation from Antarctica from this point would be very high and it will be an outlier. This is where unsupervised learning will help us. Another real world example is to find Facebook friends and customer segmentation, where customers are grouped together based on their interest. It's easy for us to target them to buy a particular product if we're able to perform customer segmentation. Now moving on to reinforcement learning. Reinforcement learning is a different beast wherein we have a learning agent, which is the robot here, which tries to understand how to perform actions in a particular environment based on repeated trial and error. We're not giving the answer to the robot directly or the learning agent directly, but we're trying to help it in terms of providing rewards and penalties in case of negative rewards. So in this instance, the robot is supposed to move towards its left and move the bucket, but it's moving towards the right, towards the fire. We're giving negative 50 points as a penalty. Now the robot understands that it's not supposed to perform this operation again. It defines a policy such that it obtains maximum reward over time. Policy is nothing but the action which is supposed to take in a given environment. Example of reinforcement learning would be self-driving cars and AlphaGo, wherein the robot tries to play the game Go with various versions of itself to understand the best method. Now moving on to performance of machine learning. Performance of these simple machine learning algorithms rely heavily on the representation of the data. For instance, let's consider that we're trying to recommend cesarean delivery for a patient. So the task is to predict whether the patient has to undergo cesarean delivery or not. Now, the artificial intelligence system does not directly go and examine the patient, but rather it's given with the formalized report from the doctor, which contains some of the important features which can correlate to obtain the required outcome, such as presence or absence of a uterine. Now the algorithm has to correlate and understand how it has to map this to the each information which is present, each and every information which is present to represent the patient is known as the feature. Now, instead of the formalized report, if we are given with an MRA report for the algorithm to learn, the algorithm will not be able to predict it well because individual pixels do not make much sense to it, and neither it can be correlated to any of the complications that might occur during delivery. And it cannot control the input in this case, but it highly depends on the representation. For instance, in the picture here, if we are trying to separate the data points which is present in the scatter plot using a line, and some data point is represented using Cartesian coordinates in the left plot, the task is almost impossible. But when representing the same data using polar coordinates, the task becomes as simple as to draw a vertical. Proceeding further to the concerns of machine learning, some of the challenges which we might face while using machine learning algorithms. Some of it is called underfitting, overfitting, and optimal. So before we dive into underfitting and overfitting, let's try to understand what is training set error and test set error. We already know what training set means. Test set is nothing but unseen data. Training set is already seen data. When the algorithm is fed in with an input instance which belongs to training set, the error which is obtained is known as training set error. And on the other case, when an algorithm is fed with an input which is from an unseen data or test set, the error rate which is obtained is known as test set error. Now, unfit occurs when we haven't provided enough data set to the algorithm and it's unable to find the pattern. So it provides high training set error, where it's not able to generalize even for the training set points. Overfit is the extreme case of underfit, wherein it is perfectly fitting all the points which is present in the training set, but is unable to generalize for the test set or unseen data. We would always be concerned about how well this algorithm is able to perform in case of unseen data. In this case, it's forming a higher order polynomial to perfectly fit in the training data. So the training error is going to be negligible, whereas the test error is going to be high. Or in other words, we can say the difference between the training error and test error is going to be high. Optimal fit is the right fit, where it's able to identify the pattern and is also able to generalize for new unseen data. Now, what are the concerns with machine learning? It's very difficult to understand which are the features which are to be extracted to solve the problem. Let's say, for instance, if I'm trying to identify presence of a car in a photograph, we'll say the easiest way would be to include presence or absence of a wheel as a feature. It's very difficult to define the pixel value of a wheel, though it has very simple geometric shape. Depending on shadow falling on the wheel, sun glaring of the metal parts, viewing angle, or any other object which is obscuring our view, so on and so forth. One solution to this would be to use representation learning, wherein now instead of mapping from the representation to the output using the algorithm, we're making the representation itself as a learnable parameter, where we're saying the algorithm, you can learn how this data can be represented so that the output is going to be even more efficient. And learned representation provides better performance than handcrafted representations, and it also lets the artificial intelligence to rapidly adapt to unseen tasks with less human intervention. With each and every information which we obtain from the data, there are a lot of factors of variation which is associated with the data. We are required to disentangle the factor of variations or disregard the ones that we do not care about. Of course, it can be very difficult to extract such high-level features from raw sensory input. And in some of the cases, For instance, let's say understanding speaker's accent. It requires highly sophisticated or human level sophisticated algorithm to understand the data. Now, where understanding the representation is as complicated as to solve the whole problem, representation learning does not seem to help us. Deep learning solves this central problem where complex task is given as a representation of simpler tasks. Complex task is built upon using simpler tasks. If we draw a graph where we say this is simple task and on top of it there are more simple tasks and then we go on to complex tasks, the graph is going to look deep and that's why it's known as deep. It's very difficult for a machine to create a function which can map the raw pixel value to a direct class. We're trying to solve this problem by dividing it into layers and understanding each and every bits and parts of the data. There are three layers. One is called the input, the other is called the hidden, the third is called the output layer. Input layer, which is also known as the visible layer, because the data which we feed into the network goes into the visible layer. And with increasing hidden layers, the level of abstraction increases. In the first hidden layer, the edges are identified, which is present in the input image. Now, the collection of edges is provided to the second hidden layer to find the presence of corners or contours. Now, the collection of corners or contours is then fed to the third hidden layer to find presence of an part of which belongs to a class. Class is car, person, or animal. Let's say collection of corners or contours gives us a wheel or a face. We can easily be able to map it to the class to which it belongs to, which is present in the output layer. We use convolutional neural network to solve lane detection using deep learning. To understand what is convolutional neural network, we need to understand what the operation convolution is going to do. Convolution is nothing but it summarizes the presence of a particular feature in an image. It also helps us to learn from the image, certain parameters from the image. In terms of convolution, the first argument is going to be the input. The second argument is going to be the kernel, which is adapted by the learning algorithm. The output is often known as the feature. Kernel can be handcrafted such that it understands either presence of vertical or horizontal image. It can either be used to smoothen or sharpen the image. It can also be used to perform Gaussian. So this kernel is superimposed on top of the input image to perform element-wise dot product, and then the outputs are summed up together to obtain the output feature maps matrix form. Now, the number of steps which the kernel will take after performing one operation, if you see here, it's first placed on top of 7, 2, 3, 4, 5, 3, and 3, 3, 2. On the second step, it skips the first column and it goes to 2, 3, 3, 5, 3, 8, and 3, 2, 8. In this case, the number of jump is determined by a number called stride. Striding tells us how many jumps it has to take when it moves from one particular instance to the other. There is another important parameter which is known as padding. Padding is important because you see here any other value other than the value which is present in the boundary is gone through multiple times. So we are trying to extract the features again and again. But the boundary values are sometimes missed out. Let's say there's a presence of an edge in the boundary and we're concerned about the edge. In this case, we might lose some information. So to retain this information, we pad zeros on the top, side, and towards the border of the input, so that now the dimension of the input increases. And when we start from the zero, we can cover these border values more than once, and that would help us retain more information towards the edge. Moving on to semantic segmentation, the task which we're trying to do, the lane detection, is going to use instant segmentation. To understand what is instant segmentation, we need to understand various computer vision tasks which are already available. One of it includes semantic segmentation. Semantic segmentation is nothing but the input is given, the output is going to contain pixel values. The output is going to contain pixel values, which is going to represent the class to which each of this pixel belongs to. So input has a spatial resolution, the output also has the same spatial resolution. But now, instead of the class value or anything else, there is each pixel value representing to which class it belongs to. Now you can see that each of it is marked as 3, 1, or 2 based on whether it belongs to plant or grass or person or a person. Each of the class is given a color, and that color is superimposed on top of the input image to segment the image based on the class to which it belongs to. The person is given red color, the person is given purple color, the plant is given green color, buildings are given yellow color, and sidewalk is provided with gray color. Now, the output image would contain each objects segmented based on colors. View of an automated vehicle would look like this, wherein each object which belongs to the same class is not differentiated, where all the cars are given same color, all the pedestrians are given same color. All that we're concerned about in this case, whether there's a car or not. Now, to be able to appreciate instant segmentation better, we can talk about various computation tasks which are already available. Let's consider an image which has only one object in this. In that case, we can say it belongs to this class, it belongs to cat, it belongs to dog. And object that is known as classification. Now, classification plus localization would include putting a bounding box on top of the object to identify where exactly the object is present in the particular image. Now we have to predict the class. On top of that, there should be an output for a bounding box which contains XY coordinates to understand where the bounding box has to start, and we can have the height along with the width to draw the whole bounding box. Now, when there are multiple objects which is present in an image, we call the task as object detection. We are supposed to put bounding box for each of the object which is present there, and even in this case, object which belong to the same class, different object which belong to the same class are not differentiated. Both of the cats are given a red color bounding box, dog is given a different color bounding box, duck is given another bounding box. Moving on to segmentation, to segment data based on the class to which it belongs to. There are two types of segmentation. One is called as semantic segmentation, the other is called as instant segmentation. Semantic segmentation is nothing but though different objects, there are different objects which belong to the same class, there is no differentiation between them. But in instant segmentation, each object which belongs to the same class is distinguished with different color. We see there, the cat, there are two cats in the picture, and one is given yellow, the other is given red to distinguish them. When we try to solve this problem using brute force method, we are trying to train a neural network and predict the output, which is going to be the class value. Now, to retain the spatial resolution of the input image is going to be computationally inefficient. And one solution to solve this problem would be to downsample the image and then upsample it, to have one upsampling layer parallel to the one downsampling layer, so that the output has the spatial information retained. Moving on to downsampling methods, we can either use striding or max pooling to downsample the given input image. The goal is to reduce the computational load, memory usage, and the number of parameters which is used, which also reduces the chances of overfitting. As discussed, stride would determine the number of jumps which the sliding window will take. So increasing number of stride will lead to decreasing the dimension of the input image. Max pool is nothing but there is a sliding window of the kernel, but it has no weights associated with it. Unlike in case of convolution kernel, it's moved through the input image and it finds whatever is the desired operation. In max pooling, the desired operation is to find the maximum in the given window. There is also min pooling, average pool. It finds the maximum in the given window and outputs it. Moving on to upsampling methods, there are various types of upsampling methods which is available, also known as nearest neighbors, bed of naives, max and pooling. We are trying to use transpose convolution here because it has a learnable parameter. In this case, we are considering an input which is again multiplied or convolved with a weight vector, which is a learnable parameter here. And the output, here we assume stride of 2. So the red box is multiplied with all the W1, W2, W3 values till W9. And the red box indicates the output which it produces when there's a dot product. With the stride of 2, we skip 2 columns, and the blue box represents the output when the second pixel in the input image colored blue is multiplied with the weight matrix to obtain the input. As the stride is 2, there is only one column which is overlapping here. So the values of the overlapping columns are added to obtain the output. Here, increase in the number of stride, there will be an increase in the dimension of the output image. In the right animation, we are considering a stride of 1 and a padding of 1. Moving on to the algorithm, the data set which is used here is called as two simple data set, which contains 6408 images, node images of US highways. The data set consists of 626 images for training, 358 images for validation, and 2762 images for testing, which is also known as two simple tests. It contains a series of convolutional neural network followed by marks pooling and upsampling and downsampling. The backwards arrow represents the backward. Here is the output image which is produced by the algorithm. Though we can see that the algorithm performs fairly well on the shadow, on presence of the shadow, or during the turnings. Another approach to the same problem would be to use recurrent neural network. Recurrent neural network is nothing but here in convolution neural network, you provide input, the algorithm learns and produces output. There is no scope of past experience which the data has based on which it can learn and implement it in case of the future. So recurrent neural network has some past experience which can be used to predict the future based on the past. Now, if you're recording this image either in 30 FPS or 60 FPS, there is no chance in which the lane would change very drastically. In that case, it will be able to perform really well in case of presence of a shadow or in turnings. Now, let us understand why is deep learning the buzzword. This has three primary reasons, beginning with the first one, increasing in the data set size. With more and more of our activities which are recorded using digital devices like computers, as we have networks of these computers, it's easy to centralize and curate them. And we've also identified that irrespective of efficiency which each of the algorithm produces, it almost saturates with the increase in size of data set. So what these deep learning models need in order to produce an efficient output would be the data set, and now we're able to provide them with more data set, with increase in digitalization. Next one would be to increase in model size, wherein we have the advancement of hardware and software capabilities, we have GPUs and more computational resources to run huge models. The deep learning model is able to perform it. Increasing accuracy, where the error rates have almost saturated, we are able to move in and perform more complex tasks like self-driving cars, wherein we expect the error rate to be highly exceptional. Even 99% of accuracy is going to be not sufficient because that 1% of error rate is going to be multiplied because millions of cars which is operating, and there will be almost a chance that every car is going to crash. It's also used in speech recognition and pedestrian identification. With that, we'll move on to some of the interesting applications of artificial intelligence. Baby X. Baby X is a lifelike simulation of a toddler, wherein the goal here is to obtain flexible intelligence, like in case of human. Skywalker hand is a bionic arm, which has more control over your hand rather than the normal prosthetic arm, wherein you can either open or grip using all of your 5 fingers together. Now, using the bionic arm, you can move each of your fingers independently, more close to your natural hand. AI to prevent blindness. There is a disease called diabetic retinopathy, which is a major cause of blindness in India. And we do not have sufficient doctors to screen patients and understand if they are in the early stages of diabetic retinopathy. So this hospital called Arvind Eye Hospital in Madurai, which reached out to a Google team and asked them to develop an AI algorithm, which they can use, which captures the image of the eyes and sends it to the algorithm, and the algorithm would be able to tell whether they are in the early stages of diabetic retinopathy, which helps us to prevent blindness. The goal which they are looking forward in near future with artificial intelligence in pharmacy is really fascinating. They say in future, there is going to be no healthcare in the future because it's just going to be AI interacting with your immune system, understanding or predicting what diseases you're going to get and developing antibodies for it. Choice is a softbot developed by Microsoft, which can interact and learn from users. Benjamin is a deep learning model who can create screenplays, who can create or generate screenplays. Sometimes it's free, and sometimes we'll have to extract to get a story. There are a few screenplays written by him, which includes It's No Game in 2017 and Sunspray. Shake Alert is an earthquake early warning system. Simon is the first robotic musician where he can detect patterns in the music, or he can also imitate your music style or music style of any performed musicians. Zappy is an AI chef in Notco. Notco is an organization which works with producing plant-based alternatives for animal protein. They believe in retaining the taste and perception. Where Giuseppe develops formulas to understand from which plant-based alternative which can extract the color, texture, so that to obtain same animal protein using plant-based alternative. Poaching is one of the major concerns in South Africa, wherein poachers approach during the night in one particular view. And what we try to do to monitor this would be to tranquilize animals, put a collar of GPS and track them manually. Even in this case, we'll be able to identify when the GPS is not moving after many days for hunting the animals down. Poachers, there's Trail Guard, which is a motion capture camera, which is an anti-poaching device, wherein it will take pictures when somebody crosses through it and processes it to see if there's a human present in the image and sends it to the team of volunteers who are constantly monitoring. The very interesting part of this is it is working really efficiently even during nighttime, where it's very difficult for us to capture image and understand if there's a human crossing during nighttime. Zoom is a pizza company where they've already automated the process of making pizza using artificial intelligence. Now their concern is they have a lot of wastage generated. So now they have developed a machine learning algorithm which crunches in a lot of information, including customer details, order trends, history of orders, etc., and will be able to produce the number of orders for a particular day. This, they believe, have led them to have a very efficient supply chain and has also led to reduced food waste. Sweeper is an automated harvester which can identify stem, leaf, and fruits. It is also able to take picture of the fruit to understand whether the fruit is ripe enough to be harvested. They use something called precision AI, wherein they say there should be efficiency which is improved in farming so that we have food for all of us. RoboRace is the first automated race car by a British startup called RoboRace. With that, we're close to the end of the presentation. Here are the references. I would highly recommend the deep learning book by Jan Woodfield. If there are any questions, please use the chat feature to drop your questions. Thank you so much.